Yeah, of course. Can I continue from here or from the beginning? Okay, right. So just to set up some notation, let us define a graph to be G that is made of a triplet consisting in a set of nodes, a set of edges, and a matrix of node feature, where basically you have for every node a d-dimensional feature vector representing the features of each node. And then the standard formulation of a graph neural network is the following recursive rule, where you start the base case by initializing the latent representation of each node to be the input features, and then by updating the representation of each node via the following operations, where you first aggregate all the incoming information from your neighbors. So you take the latent representation of your neighbor at the previous iteration, and you combine it with the latent representation of yourself at the previous iteration, updating it to the new one. And this gives you the updated node representation at layer L. And you continue for a predefined number of layers that's up to you. In this case, the aggregator function is typically a permutation invariant function, like a simple min or sum, whereas the update is instead a permutation equivariant function, like, for example, a multi-layer perceptron that is composed of a bunch of parameters that provide the new representation. But of course, many different variants exist, and we won't cover them in this presentation. At this point, it's very easy to formalize like predictive tasks. For example, you can classify a node by stacking a classification head on top of the representation of the node, or you can classify the entire graph by first pulling together the representation from every node and then putting a classification head on top of that, or you can classify an edge by combining the representation of the incident nodes and then to predict a final label for the edge. In this talk, we will focus on graph neural network. Yeah, please. Is there a question? Okay, but basically our actual focus is on graph explanation. So regardless of whether they come from a graph neural network, a graph transformer, or like the latest graph foundation model of your choice. Right, I think you're pretty much familiar with this issue that graph neural network, like standard neural networks, are black boxes. And this means that if, for example, you manage to train a very powerful GNN on like predicting whether molecules are toxic or not, you cannot really understand which features the model is using to achieve such a prediction. And this, of course, comes with several consequences for like human trust, model debugging, and regulatory compliance. But I think there is no need to convince you about this, at least in this seminar. So yeah, I'm gonna skip. I guess that you are all very familiar with a clever answer predictor. I just wanted to add an example for what it means to have a shortcut in graphs. That's quite a nice example that I found some time ago. So here the data set is a collection of compounds divided based on whether they are active or inactive against the HIV virus. And the task is to predict whether a given molecule is active or inactive. That's a very toy data set, okay? So it contains very few molecules. I wouldn't say to use this like in a standard benchmarking of graphs, but people have shown that you can easily reach a very high classification accuracy by just counting the number of nodes in the molecule. And this comes obviously from like a bias in the data collection, right? So instead of like learning some features of what makes a molecule to be active or inactive, it simply counts the number of atoms. So the number of nodes in the graph. And of course, post-hoc explainers aim to train to explain an already trained model. So the pipeline is that you can train your favorite GNN and then you plug in a post-hoc explainer to try to reverse the decision process. But what is an explanation for the graph domain? What are we talking about? And how does it look like? a very natural starting point is to look at subgraphs. So, for example, if the task is to predict whether the given molecule is toxic, a very natural thing to do is to, for example, extract the subgraph of the input that is the most responsible for the given prediction. And of course, typically, you may want small and informative subgraphs over any kind of subgraphs. So basically, the first category of explanations are like subgraphs of the input, but there exist other categories like extracting logic formulas. So here the idea is that you take your GNN and you try to extract a logic formula that encodes the same processing of the graph neural network. Actually, in this talk, we will focus only in the subgraph-based part, but I'm leaving here some references in case you are interested in knowing more. Post-hoc explainability is hard. I guess you are probably familiar with this, and also for the graph literature, there have been papers showing that, for example, random explanations can be more faithful than explanations provided by state-of-the-art explainers. In a previous work, we have shown that it is very hard to basically have a stable ranking of explainers. So if you take like explainer A, typically works very well for a bunch of dataset, but for other dataset, another explainer will perform best. So it is very hard to decide which is the state-of-the-art explainer, also because it turns out that it is model dependent. So different explainer works differently according to the model that you want to explain. And explanations are also fragile, meaning that people have shown that you can perturb the input in order to change arbitrarily the explanation while maintaining the same prediction. So you can basically manipulate the explanation almost at your will. And of course, there is also this very popular paper that advocates to go for interpretable models instead of explaining black box model, right? And in fact, basically, it may seem that you are shifting the question of can you trust your model to can you trust the explanation that is provided you. And the second one is not necessarily easier to answer than the first one. And so this brought like a wave of new approaches that instead of tackling the task of explaining a trained GNN, targeted the design of novel models, of novel architectures that have the interpretability in mind, that are often referred to anti-hoc models or self-explainable models. Again, there can be different categories in which you may want to build your anti-hoc GNN. The first one is a subgraph-based, that will be our focus. There can be also other approaches like additive models or, again, logic formulas. But we will focus on the first one. And in the first family, the most popular approach are self-explainable graph neural network that generate subgraph explanations during inference. And they are structured as follows. You have the input graph G on the left that is fed to an explanation extractor, which now produces an explanation R that is a subgraph of the input, hopefully the smallest one typically. And then there is a classifier that takes as the input the explanation and provides the final label. So in a sense, you detach the monolithic GNN inside two different modules that cooperate. And I can tell you that this framework, this pipeline, got quite popular and got extended in many different ways over the last few years. In this case, just to give you an idea of how this architecture is implemented, both modules, both the explanation extractor and the classifier, are implemented as a graph neural network, where the first one predicts the importance of each edge or of each node. This is typically kind of equivalent, depends on what you prefer. But the idea is that it predicts the importance of subgraphs. Whereas the second one performs the final task, and the two modules are trained jointly with the standard cross entropy loss for task accuracy and with some regularization losses, for example, to promote sparsity or other desirable properties of your choice. These are some results from this ICML 2022 paper that is probably one of the most well-known self-explainable architectures. And there, the results are quite promising. So, for example, if you look at this task, this is like MNIST, but for the graph version of MNIST, the explanations that this model is providing is the second row, and they match quite well the digit, the original digit, meaning that the model seems to perform as expected. And the same holds also for this synthetic data set where the explanation are actually depicting the house motifs that were implanted inside this synthetic benchmark. So everything seems to work fine, but a question that is often overlooked in self-explainable graph neural network is how good are the explanations actually? Do they look just good, or are they encoding something regarding the actual model? And it has been shown that explanations can often be redundant. They can encode redundant information. They can be ambiguous, and they can be affected by spurious correlations. However, the question of whether there exists some pathological failure cases that we should be aware of remained pretty much unanswered. But in this presentation, I will show you a failure case where explanations can be totally uninformative. And that brings us back to explanations that do not explain. Just to convey a bit of intuition, let me start with an example of what an explanation that does not explain look like. Let me consider a set of random graphs where you have a bunch of nodes that are randomly connected, and each node can have 4 colors: red, blue, green, and violet. Here there is a little caveat that green and violet nodes always appear isolated from each other and always appear once per graph. So every graph will have a bunch of red and blue nodes and one single green and one single violet that are isolated from the other. The task in this case is to count the relative numerosity of blue and red, saying 1 whenever the number of blue nodes is greater than the number of red nodes. So I hope we can agree that the green and the violet nodes are completely uncorrelated with the label because they do not appear in the ground truth function, and they always appear in the same shape across every graph. So they are completely uncorrelated with the label. I hope we can also agree that an accurate graph neural network must learn some sort of counting of the red and the blue in order to then decide which one is the most present. Now comes the tricky bit, and it's that SCGNNs can be accurate while providing only the green or the violet node as an explanation, which is in principle not possible, because if the model was relying only on the green and the violet node, its accuracy should be chance level, but it is not, because the accuracy can be even 100%. So there is something that is there is something strange going on, and this is what we call degenerate explanation, or an explanation that does not explain. And the reason is that the explanation shows you something that the model cannot do, because otherwise it will have been reached the random chance accuracy. This is an example, practical example, so a more quote-unquote real-world example with the MNIST dataset. So just to give you an intuition of how we can deal with images, but graph version, I prepared this simple figure. So you start from the MNIST image on the left, you apply a superpixelation algorithm, and then each superpixel corresponds to a node in the graph, where like the node feature are, for example, the mean of the pixel values inside the region. And then you connect region based on the adjacency matrix. Based like if 2 superpixels are close together, there is an edge between the 2 nodes. And so basically you do this procedure and you end up with this kind of graphs. And in these graphs, I trained SCGNNs on these graphs, and the accuracy is very high. It's like 97 something. And then I highlight with a yellow node, with a yellow color, the nodes that are predicted to be part of the explanation. And as you can see, the model claims to be using like background pixels. But background pixels are like the white ones are always white. Like if you inspect a bunch of MNIST images, you see that typically the digit stays like in the middle, right? So there is always like this band of constant color pixels that surround the digit, and the model claims to be using that information. But again, it's reaching a very high accuracy, so it must be looking to the actual digit to infer the label. Another example is like sentiment classification of tweets. In this case, the SCGNN is achieving a very high accuracy while providing like stop words as an explanation that again do not carry any semantic information, any sentiment information. Okay, right. So in this part, we saw that there is this problem and it can happen in practice. Another interesting factor is that these are not artifacts, but actually it turns out that it is actually the optimal solution of these models. So what we did was to basically inspect the training loss, and it turns out that we can come up with a sufficient condition such that the loss is minimal. Now, I don't want to bother you with the full theorem, I just want to give you the underlying idea. And the idea is that if you pick like a certain data distribution with a deterministic ground truth labeling function, and every time that there exists this big Z that is like a set of single node subgraph, just to give you an idea, for example, the green and the violet node in the previous example, it is possible to find a pair of explanation extractor and classifier such that the resulting self-explainable GNN implemented as this model achieves optimal true risk while providing as an explanation the elements in this anchor set that are like green and the violet nodes. And how is this possible? Well, the reason is that the explanation extractor internally solves the task. So internally it's counting the red and the blue, and then as the explanation provides something that can be completely unrelated, but label encoding. So in this case, for example, this explanation extractor is giving the green node whenever the class is 0, and the violet node whenever the class is 1. And then the classifier has an easy game in learning to map the green to class 0 and the violet to class 1, because it's a simple bijective mapping at this point. So all the work is done inside the explanation extractor, but you will never know because the explanation is the output of this model. So at the end, you still have a black box, basically.
Your question.
Sure.
On this example. So it looks like that for this to be possible, you basically need as many anchors as the number of classes.
Yes.
Or something like that, right?
Yes.
But otherwise.
True. True.
Okay.
But yeah, is this the question or you have a follow-up?
Yeah, no, this is the question. But then I was wondering, okay. If this is the case, then it means that explanations will be unfaithful only when your graphs and your data sets basically has this property, or is there something? No, well, there's something more, I guess.
Yeah, so like this is kind of the extreme case where the explanation is like this very specific anchor set, but actually in principle, you may have any super graph of this anchor set, right? And they may even change. So like in the paper, we have like an extension of this theorem that instead of showing that the unfaithful explanation achieves the optimal true risk, it achieves like the best possible loss across all the explanation of that size. So instead of having this specific anchor set, you may have even like larger subgraphs. Then the loss won't be 0, will be higher, but will still be best across all the possible explanation of this size. Does that make sense? Okay, thank you. All right, so I hope it's quite clear up to now that these degenerate explanations are actually a big problem if you want to build explainable systems, because this means that explanations cannot be fully trusted. Like it's not clear, no, or like I give you an explanation, is faithful to what the model is behaving or not. Also because a follow-up experiment that I'm gonna show you in a second shows that malicious attackers or like malicious service providers can conceal the use of protected attributes like on purpose. And the pipeline works as follows. Like the attacker can identify an innocent target explanation that wants to provide to the users, and then trains the self-explainable GNN to solve the task with the best accuracy possible while providing the designated explanation that was designated even before solving the task. So basically, the attacker has full control over the explanation that is provided to users, while the model can still behave as it wishes. Let me give you a practical example. This is like the dataset that we tested on. And for every dataset, we picked a malicious target explanation that is basically meaningless for the task. So for the red, blue, green, and violet example of before, we can pick the green node and the violet node for both classes respectively. For the MNIST case, we can pick like the top left and the bottom right pixel. Or for example, for the sentiment analysis task, we can pick like commas and dots as explanations. And now you can combine the standard cross-entropy loss of your model with this explanation supervision that instructs the explanation extractor to provide these explanations. Like this is possible. You are training the model, you can change the loss as you wish. And turns out that the model accuracy of the attack is pretty much the same as the original one. So you're not losing much information except for like one case over there, I think. But in some cases, you're even gaining some accuracy like this. While the F1 score of the explanation is very high, meaning that the model is providing the explanation that you picked, that you're forcing, while the model is still achieving high accuracy, even though the explanation that you are forcing is meaningless, is carrying no information.
How could you gain accuracy? Is that just noise or is that?
Even done.
Yeah, I think like this was pretty much probably like a failure case of this architecture, because like 41% in MNIST means that you are learning only half of the digits, right? I guess that with this target explanation, you are like providing more fine-grained supervision, no? Because you are already instructing the model to infer which is the digit at the explanation extractor level. So you're kind of giving more supervision, no, than the standard training. Does that make sense? Like, for example, if you look here, because like maybe that this bit was not clear, right? For MNIST, you're picking the top left and the bottom right ith pixel. So if it is class 0, it will be like the two corner pixels.
Yeah.
If it is class 1, you shift by 1.
Yeah.
If it is class 2, you pick the last but 2. And so this means that the position of the pixel is already label encoding, right?
Okay.
And you are providing this extra information that is correlated with the label to the model, right? And so like if the model can correctly predict this explanation, it means that it already inferred the right label. Because to predict the last but 2, you have to be in digit 3.
Yeah. Okay. Yeah.
So it's kind of like an additional supervision, and I think that in this specific case, it helped a lot the model to train.
Okay.
But that was like a corner case. All right. Actually, there is even more to say, that it is in principle even possible to prompt an SCGNNs, not to output uninformative explanations as we have seen so far, but to output highly plausible explanations that a user may be happy with, but that are drastically unfaithful. So in this case, I tried this as a side experiment where the model is providing as the explanation the actual digit. So seems to be like a success case, but the model is actually relying on some color information that I added before training. So I took the MNIST dataset, I added colors as confounders, where every color is associated to a label. So if you learn the color, you can infer the label. These are confounders. And I train a model such that it's making predictions using the confounder, but it's showing the actual digit. It's showing like plausible information. All right. At this point, the question is, you show that this problem can happen. You showed that for several models, this is actually the optimal solution. And now the question becomes, can we actually detect when an explanation is degenerate? Do we have some tools to rule out unfaithful degenerate explanation from actual faithful explanation? And like a natural way to cast this question is by inspecting faithfulness metrics. So in the explainability for GNN's literature, there are a bunch of metrics, like this one in the tables, that try to estimate how faithful an explanation is. And they work pretty much similarly to what you have like for image explanation, like you keep the explanation fixed and you start to perturb the rest, these kind of things. And actually there are two main families, necessity metrics and sufficiency metrics. And I'm gonna very briefly tell you how they work so that you can build some intuition. Let us define a graph G and an explanation R. Then a necessity metric aims to perturb the explanation. And if the explanation is necessary, perturbing it should result in a change in the output. So basically, an explanation is necessary whenever sampling perturbation that so G prime is like a modified graph that is sampled from a distribution that modifies R, that modifies the explanation, and you're happy whenever the output changes. So that's good. Sufficiency is like the dual of necessity. You apply the same operations, but instead you keep the explanation as it is, you keep it fixed, and you start perturbing the complement. So you sample the perturbed graph from a distribution that applies perturbations to the complement, and you're fine whenever the prediction is not changing. And so the previous question can be casted as follows. Given a degenerate SCGNNs, okay, so we pick a model, we pick an SCGNN that we know is providing degenerate explanation. Can we recognize that it's providing degenerate explanation? It's kind of like a detection game. And in order to do that, we took these metrics and we implemented them, and we measured how many explanations each metric is marking as unfaithful or not. The results are quite interesting, are quite surprising, in the sense that in some cases, metrics can actually reject almost all degenerate explanations. So the metric is actually aware that the given explanation is unfaithful. But the surprising bit is that for pretty much every of the previous metric, you can find at least one or two data sets where around 0 explanations are rejected, meaning that the metric did not manage to mark this degenerate explanation as unfaithful. And that's a big, how to say, it's a big hole, because then you cannot trust these metrics, right?
What's the proportion of degenerate explanations?
In this case, it's 100%. Yeah, okay. Because like we trained the model with the attack of before to output degenerate explanation, right? So in principle, the best value is 100% of labia, 99.999, that's fine. But like achieving around 0 is really like you're completely not aware that this explanation is unfaithful. But do not display it, because we propose an unfaithfulness metric. So jokes aside, we like to address this problem, we propose a new metric that we call the extension sufficiency test, that works pretty much the same as the previous one, but with like a couple of caveats more. That is, instead of like, let me recall you, like the way that the previous metric were working is that like they sample a perturbation, they sample a perturbed graph from a user-defined distribution over perturbations, and then they take the average over perturbations. Instead here, we are imposing a very specific structure that is, we aim to test every possible extension of the explanation within the graph. So basically, you have the R, that is the explanation, you have the G, that is the entire graph, and you start sampling extensions of the explanation within the graph. And then you take the maximum, that is like you take the worst case. So as long as you find a perturbed graph that witnesses a change in the output, we mark the explanation as unfaithful. So it's a more conservative metric also, if you want. And in this case, the results are much better in the sense that we are much more robust than the other metrics in spotting degenerate explanations. There are still points of improvement. For example, here we can reject only around 50% of the explanations. But at least the point that I find the most reassuring is that we are basically scoring the highest across every setting, meaning that the explanation is pretty much robust across models and across data sets, something that the previous metrics were not really able to do. And if you mean this one?
Yeah. Yeah, but you know why?
Yeah, so basically it works in a rather convoluted way. So you pick the explanation, okay? You remove the complement. You pick a random graph in the dataset and you pick its complement and you replace the complement. It's a bit convoluted. And the reason why it's not working for RBGB is that with very high probability, you're picking, actually, like you're not picking the graph from the entire dataset, but from graphs of the same class in the dataset, right? So basically, by picking another graph with the same numerosity of red and blue, you are just putting in like a new green node in the graph, but the numerosity remains the same. So the output of the explanation extractor is still the same because the label is the same. So it's kind of like it's preserving the label, so the output is the same, and you are the one putting the green violet in the node, so it's there, and the explanation extractor can provide it. Maybe it was not very clear, but I can sketch an example later if you want. And reasons for why other metrics do not always work is that like some of them, like this robust fidelity, is doing edge perturbations, like it's removing edges at random. But there might be cases where edges are not important. Like in this data set, edges are not actually playing any role. You just have to count the nodes, right? So if you start removing edges, the model might be invariant to that. And so that's why perturbing edges has no effect. Yeah, so this brings us to the conclusions, actually. So to summarize, we have shown that self-explainable graph neural networks may output unreliable explanations. And we provide a sufficient condition under which these unreliable explanations are actually the optimal solution of the SEGNN's loss. Also, we explored a case where a malicious attacker can deliberately conceal the features that the model is using, and in principle can even hide the use of protected or sensitive attributes. And the last bit is that these fabricated explanations can actually go undetected. And like we propose a benchmark to test the faithfulness metric. So this was also like a nice thing that that I liked about this work is that we are actually benchmarking the metrics. That is something that is not done very often. And we propose a novel and more robust faithfulness metric. And this pretty much summarizes our work. And yeah, I'm happy to take any question if you have. Thank you.